Hello, everyone. Welcome to the invited section of the Women in Logic 2020. It is a huge pleasure to be here sharing this section because the two invited speakers are good friends of mine and wonderful researchers and wonderful people as well as wonderful researchers. So we will start with Professor Maribel Fernández from King's College. Maribel is a professor of software systems group, of the software systems group, apparently, or at least that's what her webpage says. And that's kind of quite exciting because I think the theory work sometimes wants so much to be systems work, and I think Maribel is one of us that actually can do it. There's a message about. There's a message. Yes, no, okay. So you know, Maribel is one of the very successful people that can do theory and systems at the same time, and I think. You are on sabbatical this year, Maribel, aren't you?
Yes. So I had half a year of sabbatical and half a year at home.
And she has this beautiful picture of London behind her. And I mean, I'm better unfortunate that your sabbatical coincided with a pandemic, right? It's not. No one knew that was going to come. So I think we just kind of have to try to make the most of what we have. And so please talk to us about nominal syntax with atom substitutions.
Okay, many thanks, Valeria. And I want to thank everybody. I want to thank the organizers. It's not easy to organize things in these conditions. And it's really great that we can still meet, not in Paris, but at least we can still meet and we can see each other. And I'm really very, very happy to be talking here with you. And yes, what I wanted to tell you about today is a work that I did with Jesus Dominguez. So he was a PhD student, now he's a postdoc at King's. And his area, his PhD was about an extension of nominal syntax. So in this talk, I'm going to try to introduce nominal syntax and then talk about this extension that we studied with Jesus, which adds substitutions into the syntax. So let me see. Yes, so first an introduction. It's a little bit technical because I need to introduce the syntax, but it's not very different from things like the lambda calculus or higher order abstract syntax, which many of you have already seen and was mentioned in previous talks. So the intuition is that this nominal syntax was introduced to simplify dealing with systems where there is binding. So the lambda calculus is an example, but you have many. So first order logic probably is the best example because you see there you have the for all, you have the existential, and we introduce this to our students and we explain to them that obviously the name you put in the for all or in the existential variable doesn't matter because they are binders. So there we have this notion of alpha equivalence. In the lambda calculus you have it too, but in the lambda calculus there's also beta. And we tend to kind of brush aside alpha equivalence and focus on the beta rule. Whereas in the nominal syntax, really the main focus is the alpha equivalence relation. And so we are interested in particular in the reasoning, equational reasoning in languages with binding. And in particular, the problem of unification, which is you want to know if two expressions, two terms in that language can be made equal by instantiating variables. But if you have alpha equivalence, then you want to know if they can be made alpha equal, not just identical syntactically, but alpha equal. So this is nominal unification modulo alpha equivalence. And it was studied by Urban Pitz and Gabay already in 2004. They showed that if you just want to focus on alpha, then nominal, then unification taking into account alpha is decidable and unitary. And this is in contrast with, for example, unification in the lambda calculus, where you try to make two lambda terms equal, but modulo alpha and beta, and there it's undecidable. But if we say, if we ignore beta and we just focus on binders and this notion of alpha equivalence, things work in an easier way. So we have a decidable problem, unitary, which means that if the problem is solvable, you have just one unifier that represents all the possible solutions. And there are also efficient algorithms to find that solution. So you can find it in polynomial time. If you're interested in matching, which is what you need, for example, in functional languages or to implement rewriting, it's even linear, which is the same time complexity as matching in syntactically. So this result of decidable in unitary unification started a line of work where people started to say, okay, maybe we can then use this kind of languages in logic and functional languages to include binders, because we tried before to include things like the lambda calculus, so to go to higher order syntax, but there was that problem of the undecidability, which you can also find restrictions that are decidable, but here there's no need to put restrictions, it is decidable. So that's very good because you have, as I said, all you need to work with alpha. But you don't have beta. So if you want beta, you need to define it. But you also don't have substitution. So if you wanted to define beta because you want to, for example, model the lambda calculus or parameter passing in a programming language or something where you want to have that sort of rule. So here is in this line, you see the beta rule. It's an application of a lambda term. So this syntax with brackets here is the notation in nominal languages to say that we want to bind A, okay? So this is why I was saying in nominal syntax, we work modulo alpha. So there is a notion of binding a variable. We call them atoms. So lambda uses a bound A. And if we apply a lambda expression to some term x prime, the result will be the body of the lambda x, where we want to substitute A with this x prime. But this notion of substitution doesn't exist in the nominal syntax, so you need to define it. Like we define beta with a rule, we can define the substitution with rules. So this resembles a little bit, people have been working with explicit substitutions. So the lambda calculus, where you explicitly define how the substitution works. So here we are doing that. We are explicitly defining how the substitution works. So for example, we are saying, if you want to substitute A by X in A, then you get X. The only difference here with respect to the standard explicit substitution calculus is that the standard calculus uses the Brown indices, or you need to do something because you don't have alpha normally. Here it's an explicit substitution calculus, but because we are in a language that knows about binding and alpha, we don't need to worry too much. For example, we have this rule here. If you want to move a substitution for A inside a lambda expression, so all you need to check is that B, which is the bound variable for the lambda, is not free in Y. So this notation, B, we read it B fresh for Y, and it just intuitively is saying B doesn't occur free in Y. Therefore, I can move the substitution into the body of the lambda. And you might say, and what happens if B is actually in Y? What do I do? Well, in nominal syntax, you have this notion of atoms, and atoms are, so there are an infinity of atoms. You start from the assumption that you have infinite atoms you can work with, and atoms are all equivalent, so that's why we call them atoms. They don't have properties in themselves, they are only names. So A is a name, B is a name, and each time I write something about atoms, the actual name I use in my definition is not important. So if I write this rule here using the names A and B, like I wrote this one, for example, for the name A, that means for any atom A, I can do this. So if I want to substitute in B, B for X, this also applies. So this rule, I chose to use A, but because in nominal syntax, as I said, atoms don't have, A doesn't have any property that B doesn't have. Okay, so when I write a rule for A, this rule exists also for B and for C and for D, for any atom. And similarly here. So if Y happens to, if the instance of Y where I want to apply this rule happens to have an atom B which is free, well, instead of this rule, I use the same rule, but with C here, okay? So actually, the systems that we write when we talk about nominal syntax are defined modulo something we call equivariance. Equivariance is a property of nominal logic, of nominal, says what I've just told you, that you can change the names of the atoms if you want, okay? Any property you define should work also if you choose different names for your atoms. So nominal languages have this kind of syntax where you have the notion of an atom, variables, but the variables is like first order, and function symbols is also like first order logic. They are like constructors for expressions. They don't really have any meaning by themselves. The interesting thing is that you can decide to bind an atom by using this notation. And once you define your language, you can define rules or functions or clauses on them. And it has a formal semantics which comes from nominal sets. So what we wanted to do in the work with Jesus is try to simplify a little bit more the work, for example, here to define the lambda calculus. So we don't have to worry about alpha because that's part of the nominal language, but why do we need to worry about the atom substitution? Couldn't we, since atom substitution is something that happens not just in the lambda calculus, but in other contexts too, you might want to, for example, in logic, in first order logic, you might want to, you have an existential clause and maybe you have a witness. So you want to replace the existentially quantified variable everywhere in your clause with that witness that you found for the formula. So this notion of replacing a bound variable by something, it's useful not just for the lambda calculus. So we thought maybe we can actually try to define a version of the language that includes this as a primitive, okay? So we did that. We added non-capturing substitution so we built into the language the rules that define the atom substitution. And we looked at what happens then with matching and unification. And we found that matching remains decidable, but it's now finitary, not unitary, which means that you don't have a unique solution always. There are some problems that have multiple independent solutions. But we can restrict the problem to make sure that there is a unique, most general solution. However, with unification, once we add a built-in non-capturing substitution, the unification becomes undecidable because, well, we showed that we can encode Hilbert's 10th problem. And it's a similar situation that happens with second order unification. It's also undecidable. So there is some relation between unification, nominal unification, where you built in the non-capturing substitution, and second order unification, but as our next job to do, we need to really check what the relation is. So let me recap a little bit. So we have a syntax in which we have primitive notions of an atom. And this is a primitive thing because, as I said, the semantics of this language comes from nominal sets. And nominal sets have atoms as a primitive thing, a primitive notion. We also have variables. They are just the same thing as the variables we have in first order logic. Sometimes people, instead of talking about atoms and variables, they talk about variables and meta-variables. That's the people that are used to working on higher order abstract syntax. But for us, we follow this terminology of atoms and variables. Term formers, like you have in Prolog, you can use function symbols to build expressions. The novelty is this abstraction construct that we can use to bind an atom in a term. And then, because we are working with atoms, and I'll say we come from nominal sets, atoms, I'll say, they are not structured. They don't have anything in themselves. They are just names, and we can swap them. So we can replace, for example, an atom B with another atom A. And what this does is just swap A and B everywhere. So look at T, the term T as a tree, and you just swap the names A and B everywhere in T. Another thing that you have also as part of the language is the notion of freshness. So we can say that a certain atom is fresh. It means really it doesn't occur free. That's what freshness means, but it can be formally defined, of course. And this last thing is not part of the nominal sets or the nominal language, but it's the thing that we added in this work, the non-capturing atom substitution. So formally, the language is just a language of expressions, terms with atoms. What I told you before, F as a constructor of expressions, F of S can be a tuple. This is the abstraction. These are the variables that are like first order, but I said like because since we can instantiate them with things that have atoms, so X could be replaced with A, for example, or with something which contains atoms, I can specify that once I know which instance I'm looking at, I can apply a change of name. I can do renamings, I can do permutations. So pi is a permutation of atoms that exists in nominal logic. And then this is the extra thing we added is an atom substitution. So atom substitutions and permutations of atoms, we say they are suspended on variables. They're waiting there when we know what the variable means, what this unknown term is, the permutation and the atom substitution will apply. So a permutation is in our work represented with a list of swappings. You could use other representation for permutations, but this is convenient. So it is the identity permutation. So a permutation is just a mapping, a bijection between atoms. So you can represent it, as I say, with lists of swappings. And an atom substitution formally is a mapping from atoms to terms, also with a finite domain. So this is our language. And you can build terms like, for example, map. You can imagine constructors for lists or, well, the language is user-defined, so you put what you want. But I told you there is a formal definition for freshness of an atom in a term, and it's given by this set of rules. You don't need to look at the rules in detail. It's basically just telling us that A is fresh if you abstract A. So really, this is why I was saying the intuition is that A is fresh if it occurs free. Because if it is abstracted, A fresh means it doesn't occur free. So, okay, so A fresh in an abstraction for A. So A is not in the abstraction because the abstraction defines an alpha-equivalence class of terms. So A is not free here. A is not free in B. A is not free in abstract B in S if A is not free in S, etc. Okay, so this is an inductively defined relation. The only situation where it's more difficult to know if A is fresh or not is when you have a variable, because you don't know what the variable is representing. It's an unknown term. So how do I know if A is fresh in this unknown term? Well, there is a condition here which basically tries to check what pi, the permutation, and the substitution will do, and try to check that they will not, either X is not instantiated with something that brings an A, or the A will not come because of the swapping or substitution you do. So it's a formal definition, but intuitively it's just asking to check that A really is fresh in that term. And similarly with alpha equivalence, we can define it formally as an inductive relation. So A is alpha equivalent to A. So all the rules are what you would expect. The interesting one is this one. How do you know if the abstraction of A in S is alpha equivalent to the abstraction of B in T? And this is where swapping names is useful, because what I can do is I can change in S the A's to B, okay, because T is an abstraction of B. So let's see what happens if I change the A's to B. Do I get the same thing here? Okay, so that's why checking alpha equivalence, if you have this notion of permutations of names, is quite handy. You also need to check that B is fresh in S, because clearly if B was free on S, then this cannot be equal, since B is not free in this part, okay? We know B is not free here, so B cannot be free in this. So that's what this says. And then here is just checking inductively that the terms are equal. And again, all the things are just inductive. The difficulty again comes from the variable, because how do I know that these two things will be alpha equivalent, since I don't know yet what X will be? So I need to make sure that no matter what I put in X, these two things will be alpha equivalent. And that's why the condition is complicated, because I need to check what pi and pi prime, those are atoms permutations, and phi and phi prime, which are atom substitutions, what will they do with the atoms that come in X? But okay, it's just a formal definition, and the intuition, I think, it's just the familiar alpha equivalence relation that we know. We want to make sure that if we just ignore the names of the bound atoms, then the terms are equal. The atom substitution is a bit difficult to define in general, because you need to make sure that you respect this notion of alpha equivalence. So for people that are familiar with the lambda calculus, you know that when you define the atom substitution, you need to avoid capture of free atoms. So that's why we have also a definition which is inductive for atom substitution. But in the particular case where you're dealing with an abstraction, so you want to make a substitution on an abstracted term, that's why you need to make sure that you pick a fresh name. So we pick a fresh B, and we try to do the substitution inside the abstraction, but we know there will be no capture because we took a fresh B. And the reason why we can always find a fresh B is what I was telling you at the beginning, that in nominal sets, there's an infinite number of atoms. And also, by definition of nominal set, each term can only mention a finite number. Okay, so there's an infinite set of atoms, and in any expression in your language, you can only use a finite number, which is quite natural because all our expressions are finite terms, are finite size. So for this reason, it means that whatever expression you write, there's always some atom that is not free there. So whenever you want to pick a fresh atom, you can always find one. So that's why we can make this definition and make sure the substitution is non-capturing. So that's the atom substitution, by the way. Here we are really substituting atoms. But so in our notation, it's like this. For instance, the atom C is substituted by 0. But we can also substitute variables, and that's like in first order logic. If you want to substitute a variable, you graft a term in that place. So you replace it by a term, and there, if something is captured, well, it is. It's more like, again, for people that are used to the lambda calculus, it's what happens with a context in the lambda calculus. When you have a context and you substitute the whole in the context with a term, you can capture atoms, okay? So the variables in nominal logic are like that. They are just representing some unknown term. When you want to replace them, you just put whatever term you want in that whole, and if things get captured, that's fine, okay? So for example, here, I got a substitution of x for a in a term that has an abstraction for a. Well, I just put the a in the place where x is, and now a will be captured. Okay. So we have two notions of substitutions. This, the variable substitution, that's the usual one in nominal logic. And we introduced also the atom substitution, which that one is non-capturing. And now we look again at what can we do if we need to unify expressions. The reason why we are interested in this is because, as I mentioned at the beginning, if you want to define, for example, some kind of computation on these expressions, rewriting or a kind of logic programming language or a functional language using these expressions, you want to make sure that matching or unification work properly. Also for theorem proving, if you're just doing equational reasoning with these expressions, again, matching and unification are useful tools. So we looked at unification and matching in this extended language, and we realized, first of all, that the notion of solution changes because nominal unification, like first order unification, has unique, most general solutions. But here we realize we need to talk about families of solutions. So you can have even infinite principal solutions. In an expression like this one that I have here, so I have a term on this side, it has f at the root, f of a, and then some unknown subterm here, which has a suspended atom substitution. So when I know what x is, if it carries a c, if it contains a c, it needs to be replaced with b. And on this side is an unknown term x that if it contains a c, I'm going to replace it with f of ab. And here you can make these two things equal by, so you can add as many f's as you want. So if you put in x something of this form, f of a, blah, 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 many f of a, c, they will be equivalent because on this side, you will have one more f of a, and then here the x, the c will become b, okay, because there's this substitution. And on this side, well, you replace x with f of ab, so in the end you will have the same number of f's on both sides, many a's, and a b at the end. And because you can choose what number of f's you want, this will work for any number of f's, each of these substitutions is a principal solution. They are also incomparable. They are not, you see, they are ground substitutions, so they are not instance of each other. They are independent solutions. So we have an infinite number of principal solutions. This sort of thing doesn't happen in nominal unification, but you don't have in nominal unification, you don't have suspended atom substitutions. So it's this extra thing that we added that is causing this behavior. And for the same substitution solution, you might have different freshness contexts that help you to get the equality. So here, for example, when we are trying to make these two terms equal, we can make them equal by requiring b not to appear in x and a and b not to appear in y. Then this thing doesn't do anything, and these things here don't do anything. Or you can just say b and c cannot occur in x. If b and c cannot occur in x, this thing will never do anything, and this will never do anything. Okay, so you will get xx. So there are situations that we didn't have in nominal syntax, but occur when you add this substitution, this atom substitution. And with respect to matching, is a bit easier. So matching is the problem, it's like unification, but one of your terms is constant, is ground. Okay, so in functional programming, for example, you have your functions, imagine Haskell or Camel, you have your cases, and you have an expression which is ground, and you try to match your expression with the left-hand sides of your rules. In our case, matching is decidable, but you again might have different ways of matching your term. So there is an advantage in the language because you now have this atom substitution built in. So if you wanted to define the lambda calculus, then you can define it just with one rule. You don't need to worry about the explicit substitutions and all the things I was explaining before. But there is a price to pay for that extra convenience, which is that now you have a more complicated situation with respect to matching and unification. So we tried to see if there was a way of finding a kind of compromise situation where you get some of the advantages and not a price too high for those advantages. And what we did is we designed an algorithm for matching, which I'm not going to go through. Unification and matching algorithms can be specified as simplification algorithms. So you start with a problem, which is your set of expressions you want to unify or match, and then you apply rules to simplify your problem. This kind of presentation is I think, probably one of the first is the Martelli-Montanari algorithm was presented with this kind of simplification rules. But if you look at the surveys of unification, it's quite standard to do this. So you have rules like clashing rules. So if S and T have different heads, then you can say there's no solution, elimination of trivial equations, decomposition, if they both have the same thing at the root, then you continue. And you go like that. In our case, because we have abstraction, so if you have to unify an abstraction on A and an abstraction on B, you have to do that trick that I explained when I gave you the inference rules. But it's the same idea. We have a definition of equality, which is inductive. We turn that equality into simplification rules, and we use that to solve our, in our case, matching problem. We do it in two phases. We first simplify all the equalities, but when we simplify the equalities, we can introduce freshnesses. Like here, for example, we said that abstracting A in S is the same as abstracting B in T. If when I swap A and B in S, I get T, but also B has to be fresh for S. So now if I am trying to solve this, I have to know how to solve also this kind of freshness constraints. But I gave you also an inductive definition of freshness. So we'll do the same trick, which is apply simplification rules for freshness. The really complicated part is in this slide, which is what do we do if we are faced with an equation that has variables? Because here is where we need to kind of guess a solution. And here the variables have suspended permutations and atom substitutions. We need to somehow compare the permutations and atom substitutions to see if we will get something equivalent on both sides. There's also one thing here I didn't mention in the previous slide, is that because we are trying to do matching, so I said that one side of the problem is like a constant, is ground. We cannot instantiate it. We need to know which variables are the ones that we cannot instantiate, okay? So in a functional language, you would say the thing is ground, so there are no variables in your expression. But in rewriting, we sometimes want to rewrite an expression with variables, okay? So if the expression you are trying to rewrite has variables, you need to protect them. They cannot be instantiated. Only the variables in the rules can be instantiated. That's why we parameterize our algorithm with a set of variables that cannot be instantiated. So you see that X in all our arrows. But as I was saying, yes, so we have some auxiliary functions, we call them psi and cap, to try to look inside the substitutions that we have here and to compare to see if we can manage to make these two things equal. And similarly, as I said, we have simplification rules for freshness because they are created during the simplification of equations. So we proved that this algorithm is sound and complete. These are our auxiliary functions that I'm going to skip. And for example, this, which is similar to one of the first examples I gave you, happens to have five solutions computed by the algorithm. So for example, the first one says, if you want these two to be equal, you can, so this symbol here means that I can instantiate this side of the equation. This I cannot touch, okay? So I can change x to z, okay? And I can ask A to be fresh, then this substitution will not be able to do anything because A cannot occur free in X. And in that case, then, sorry, in Z, so in X. So this works. It means that the substitution will not apply and I get ZZ. But you can also get a solution by saying, replace X with Z and replace Y with B. And then you get Z with A substituted by B in both sides. So there are different ways of getting solutions. And you can simplify them a little bit by merging. If there are two solutions that have the same or alpha-equivalent substitutions, you can put them together. If there is in your family of solutions one of them that doesn't need any freshness, then you can pick that one. And that way you can simplify a bit the family of solutions, but you still cannot reduce it to only one. We managed to find a way of reducing it to only one by putting a restriction on the kind of problems. So I'm going to try to complete this, and I think I'll skip the next part. So the restriction we put is to require that for every variable in the problem, every variable that you can instantiate has an occurrence, which we call simple. It's an occurrence that doesn't have any atom substitution suspended, okay? So in that way, we can try to find what the X is by using that occurrence that fixes the instance of X. It doesn't have an atom substitution, so we don't have to worry about that. And if for every variable we can do that, then we can find a unique solution. But as there is a restriction, because we are requiring that for every variable in the problem, there is an occurrence that doesn't have a suspended atom substitution. But with that restriction, we have unitary matching, meaning unique solution. So that's for matching, but as I said at the beginning, unification has some issues. So we can't have an algorithm for unification, because actually we proved, we thought we could, we tried, and then people pointed out, Jordi Levy, who is an expert on second order substitution, he pointed out that maybe we could look at the undecidability proofs for second order unification and see if that kind of proof could be redone or encoded in this language. And it turns out that yes, we could do a similar proof. So the encoding of Hilbert's 10th problem requires to encode addition and multiplication in your language. Because if you can do that, then you can encode Diophantine equations, which are equations between polynomials using multiplication and addition. And if you can encode this problem, then that's a well-known undecidable problem. And yes, unfortunately, or well, it's just fact of life, we can encode addition of polynomials and multiplication of polynomials in this language because we can encode numbers. First of all, we encode numbers as terms of this form. So this is the encoding of the number 3. So it is actually a sub-language, the language that uses substitutions and atoms, basically. So numbers have this encoding. They are tuples with a number of A's. So if you want to encode the number 3, you put 3 A's and a C at the end. We have a way of ensuring that you only use numbers in a problem by putting this equation. This equation is only solvable with things that represent numbers. And using this and then an equation that encodes addition. So this one is solvable only if you take x to be the number n, xi the number n, xj the number m, and xk the number p. That's the only solution. So this encodes addition. And you can encode multiplication, which is much harder, but it can be done. And because we can encode addition and multiplication and we can restrict to solutions that are natural numbers, we can represent Diophantine equations. And then clearly we can't have an algorithm for this. So it's a negative result. Unification is undecidable when you add this kind of extended notion of atom substitution. But on the positive side, matching is still decidable. You can restrict to languages that have even unique, most general solutions. So that's already something to work with. And there are obviously some kind of restrictions that we could also put in the unification to make it decidable, but that's our future work. So I think I'm going to stop here. I don't know if there are any questions.
Oh, thank you very much, Maribel. That was lovely.
Thanks.
I'm sure there are questions. So I think we can have one or two quick ones if people want to ask. I mean, I have to confess that I did not get totally what is your personal conclusion about, is that a bad fact of life, the fact that it's undecidable, or it's just that we want to have a slightly different theory of alpha conversions that perhaps doesn't use the same kind of, the two different kinds of substitution? What is your personal gut feeling about it? I mean, why did you want it for, and how are you going to cope with it?
Okay, so why we wanted to have it built in, it's because in a lot of situations, people are working with systems that have this idea of substitution. And if you don't have it built in, you have to define it yourself. So you can do that. And we do have a system. So systems like this one that I put in this slide were perfectly okay. So you can implement the lambda calculus using this system. So you implement the substitutions, but obviously you need to put the rules there for the substitution. So our situation was, there are systems in which the substitution is built in. So if you, for example, put the lambda calculus in your language, like they do in higher order abstract syntax, they work modulo the lambda calculus, then you don't have to worry about this because it's part of your language. So I guess the idea was to explore what's in between. If you don't have the full lambda calculus in your language, you only have alpha, can you include a little bit more to have some more convenience in terms of you use the built-in substitution rather than define it yourself, but at the same time, can you stay in something manageable? Because if you add the lambda calculus in your meta language, everything is undecidable. Okay, so what could be, so the nominal languages are very nice because everything is decidable, same complexity as in first order logic, and you have alpha. You don't have atom substitution, you don't have beta, but everything is nice and decidable. So it was really trying to see in that kind of scale, first order plus alpha, all great, add beta, all undecidable. What is the middle ground? And adding atom substitution, if you are just interested in matching, it's fine. It's still decidable. You can even be unitary if you remain in that language which I described. But as far as unification, then if you really want to have unification, then having this sort of atom substitution causes some problems. So I guess it was just to explore the expressive power and where the boundary between decidability and undecidability is.
Well, yeah, that makes sense. Thank you. I'm not seeing any questions. If anyone has it, should mention it now.
Shall I stop sharing the screen?
Yes, please. I think that would be good.
Okay.
Thank you. Okay, I think we can then move on so that we don't get delayed. I mean, we started a bit late, but I mean, as usual, Maribel, you just kind of put us in the right lane again. Thank you very much.
Thank you.
Thank you.